as you have noticed, looking at past trials, past HSC papers, when it comes to the harder extension 1 work, circle geometry is always there. So let's just have a bit of a recap of some of the ideas, but some of the key ideas that we see in extension 1. You see more of using the theorems in converse, like proving something is a cyclic quadrilateral, that sort of thing. So any theorem can be used in reverse. For example, the circle whose diameter is the hypotenuse of a right-angled triangle passes through the third vertex. Well, that's just angling a semicircle, is all that is. So if you've got a right-angled triangle, it's always going to be possible to draw a circle around that. And AB would, of course, be the diameter. Okay, so we can say, well, yep, AB and C are concyclic, with AB being the diameter. The reason? Well, we're using the converse of our angle in a semicircle theorem. This one, look, if an interval AB subtends the same angle at 2 different points, what are we talking about? It's that sort of situation, where from 2 points, you get the same angle subtended at 2 different places. Then that must create a cyclic quad. So AB in this case, it subtends alpha at P, it also subtends alpha at Q. Then that must be a cyclic quadrilateral, because what we're basically looking at is angles in the same segment are equal. Cyclic quadrilateral, well, you got the quadrilateral, and you notice the opposite angles are supplementary, therefore, and so on. So using the circle geometry theorems in reverse, or the converse of them, is, I guess, a common theme in extension 2 type circle geometry questions. The 4 centres of a triangle, it may be useful, it may be not useful. You might never use it, but just as what they are. The angle bisectors of all the vertices are going to be concurrent at what we call the in-centre, which is the centre of the in-circle. So there's a triangle. If I was to join up, there we go, all 3 angle bisectors will meet at a point. And if you were to put a compass on that point, it would be possible to draw a circle inside the triangle. Now, why is that possible? Because if you remember with our circle geometry theorems, we have from an external point, if you draw tangents from an external point, it creates an axis of symmetry. And so that's basically what we got there. There's an external point. That red line becomes axis of symmetry, gamma each side. Same at each of the points. And so that's why it's possible to draw a circle, and each of those sides becomes a tangent to the triangle. Perpendicular bisectors will also be concurrent. Let's draw that one up. There's a triangle. If I was to draw in all of the perpendicular bisectors, so I'm not talking about the altitude or the perpendicular height, it doesn't necessarily go through the vertex, you'll notice. It's from the midpoint of a side at right angles to it. That's the circumcentre, because now it's possible to draw a triangle that goes around it. And the reason for that one is we know perpendiculars from the centre will always bisect a chord. So the sides of the triangle have become the chords, and we said it was a perpendicular bisector. That's in fact one way of how you would locate the centre of a circle, by the way. All you have to do is draw in 2 chords, draw in the perpendicular bisector of those lines, and then the intersection must end up being the centre of a circle. Okay. The medians, they're also concurrent at a point that's called the centroid. So let's draw this one up. So the median is the one that comes from the vertex to the midpoint. What's useful about that? I guess it's the ratio that's useful, because the centroid will trisect each of those lines. So law would be in the ratio 2 to 1. 2 to 1. And then finally we got the perpendicular heights. They also are concurrent at what we call the orthocentre. So there's the perpendicular heights. Orthocentre. Now, here's the interesting thing. The circumcentre, the centroid, and the orthocentre are concurrent. Should be collinear, shouldn't it? Yes, because 4 points can't be concurrent unless they're the same point. Collinear is what I should have said, yeah. Interaction between geometry and trig. In the junior school, of course, we think of geometry as one topic, trig as another topic, coordinate geometry as another topic. But of course, we can use ideas from anything, anywhere. And there is a really good interaction. The sine rule, of course, is in fact not what we usually see it as we first see it back in year 8, year 9, whenever it is. It's actually this. A over sine A is B over sine B, C over sine C, but it will equal the diameter of the circumcircle. So let's prove that. There's a triangle. I've drawn in the circumcircle. Circumcircle. So circum means surround, so circumference. So it's the circle that surrounds the triangle, circumcircle. Now, I've drawn in the diameter and then joined the other point of the diameter up to B. So we know that angle A will equal angle P because of angles in the same segment. So therefore the sine of A must equal the sine of P. Now PBC, because I used the diameter, ends up being a right angle, because angle in a semicircle. So the sine ratio in that one, I can actually say the sine of P is BC over PC. And rearranging that, I get BC over sine P is equal to PC. Well, therefore, PC is BC over sine A, or A over sine A. So PC, the diameter, is equal to A over sine A. I could have done it with any angle. I could have said B over sine B. I could have said C over sine C. All right, let's have a look at some questions. Quite an old one now, but it's a nice question. Diagram. AB is a fixed chord. P is moving along our circle, along the circumference there. And AC and AD are perpendicular to BP and AP. The first thing is the traditional sort of question that you see in Extension 2 paper, show something's a cyclic quadrilateral. It's a very common type of question. So ABCD we want to show as a cyclic quadrilateral. Well, BDA, they've given us 90 degrees. They've also told me ACB is 90 degrees. That's information given to me. Well, that's enough to say it's a cyclic quad, because it means they're both angles in a semicircle. And it must be the same semicircle. Angles in the same segment are equal, I'm using there. And AB, therefore, is the diameter of that semicircle. Okay, so that was probably the gift mark, I guess, of the question. So now we're going to show triangles PCD and APB are similar triangles. Well, APB is equal to DPC. Basically, it's the same angle. PDC is the same as PBA, because now that I know that that's a cyclic quad, I've got exterior angle of a cyclic quad. So therefore, it's similar. You only need to show two angles of the same to show similarity. So triangle PDC is similar to PBA. Well, equiangular or angle or whatever you want. All right, so we now know those two triangles are similar. As P varies, we want to show that CD, it doesn't matter where we put P, it'll always be the same length. Always the same length. Right. There's the two triangles that I just proved are similar. I'm going to draw them outside so I can match up ratio and sides and things like that. So I'll put them in the same orientation. Now, the ratio, therefore, CD corresponds to AB in the other triangle, and PC corresponds with AP. So they would be the ratio of our sides in similar triangles. Now, if I just look at triangle PCA, triangle PCA is in fact a right angled triangle. So PC over AP would be the cosine of angle P. So therefore, substituting in the other ratio, CD over AB is also equal to the cosine of P. Remember, we're trying to show CD is constant. Well, CD is equal to AB times the cosine of P. But we said AB was of fixed length, so that's not going to change. And the other thing about P is it moves around, that angle is not changing either, right? Because angles in the same segment are equal. So angle P will be a constant value. AB, they told us, was a fixed length. So therefore, CD is a constant. Now, we're going to find the locus of the midpoint of the side CD. Right, we know ABCD is a cyclic quadrilateral. We know AB is a fixed length and it's a diameter. We also know that CD now, it doesn't matter where we put P, CD is a fixed length as well. So M is the midpoint of CD. O is, I'm going to call the midpoint of OB, which also would be the midpoint of the circle that goes around our cyclic quad. OM is constant. Equal chords are equidistant from the centre. So CD, which we said was of fixed length, it doesn't matter where we put it, so that chord will always be the same length, so therefore it will always be the same distance from the centre. So I now know that the distance from the point M to the point O is always a constant amount. What's the locus? Got to be a circle. If a point moves so that its distance from another point is always the same, it's a circle. Will it be the whole circle? M's a fixed distance from O. I'm going to find the radius, and I might have gone a little bit crazy here. But OMC will be OC squared minus MC squared. Now, OC squared would be half of AB. We said MC was half AB cos P. Possibly more information than they were looking for. But OM squared would be a quarter AB squared sine squared P. So OM, or the length of OM there, is a half AB sine P. And so my locus circle, centre O, radius half AB sine P. Would it be the complete circle is the next question, because when P then goes to the other side of the chord, is it going to be the same circle or will it be a different circle? Well, they're saying find the locus of M as that chord CD moves. Now, we were assuming, of course, for all that the CD was always on the above the chord AB. If it's below AB, what's going to happen? The angle P will now become 180 minus P. So cosine of 180 minus P would just be the negative of the cosine of P. So as far as magnitude goes, the length would still be the same size. So it doesn't matter, therefore, whether CD is above or below. The length of the chord will be the same. All right, let's have a look at a more recent one. 2008. Okay, and this one. P, Q and R are all in our circle. Tangent of P and the secant QR intersect at T. Bisector PQ meets QR at S so that QPS and RPS are both theta. Intervals RS, SQ and PT have lengths ABC respectively. Show that angle TSP is equal to angle TPS. So TSP and TPS. Well, RQP and RPT are the same. Alternate segment theorem, what am I talking about? So RQP and RPT. Now TSP is equal to RQP plus SPQ, exterior angle of a triangle, SPQ. So TSP is RPT plus theta. So RPT plus theta. So SPT is equal to RPT plus theta. So SPT is equal to TSP. Hence show that 1 on A is equal to 1 on B plus 1 on C. That's a little bit more interesting for a circle geometry question. There's the diagram again. It's going to help to have that to refer to. Okay. We now know triangle TPS is isosceles. Right. It's got two equal sides. So ST is equal to little c. Now, PT squared will equal QR times RT. That's our square of a tangent is equal to the product of the intercepts idea. So PT squared is C squared. Now, QR would be the same as C plus B. C plus B is in fact Q. Yep. And RT is C minus A. Right? So we have C plus B, C minus A. Expanding out the right-hand side, cancelling the C squareds, I now have BC is equal to AC plus AB. So I actually now have the result. You might not see it, but all I got to do is divide everything by ABC. Divide everything by ABC, and BC becomes 1 on A, AC becomes 1 on B, and AB becomes 1 on C. All right. Look, in Patel, 10C is an exercise on circle geometry.